Friends, in this video we are going to continue in geometrical properties of sections. Today we are going to start with theorems in geometrical properties of sections. So first we will understand theorem of parallel axis. First, what does it say is, uh, if you want to take any moment of inertia of any lamina with any axis in the same plane, okay, parallel to the axis of the lamina, okay. So if you want to take the axis are at a distance apart from each other at h, a lamina is having an area a, and the centroidal axis, you can say g1 to g2, passing from g, which is nothing but the center of gravity or centroid of that particular lamina. You can see the formula at the bottom. What it is saying is the moment of inertia about an axis AB. Okay, so AB axis is lying at the bottom of the lamina, right? So, but it is in the same plane. Okay, just imagine AB axis and G1 G2 axis is lying in the same plane, and both are parallel to each other with a distance of h. So moment of inertia of that particular lamina, if you want to take moment of inertia about AB for that particular lamina, you have to take what? The sum of moment of inertia of that lamina about the centroidal axis, that is moment of inertia passing through G, that is G1 G2. Okay, so that moment of inertia you have to sum up with the product of the lamina, area of the lamina, and the square of the perpendicular distance between two axes. Okay, so that distance which is there, h, it should be squared, and area of the lamina should be multiplied. So this product, area of the lamina and the distance square, that is h square, should be summed up with moment of inertia of the lamina about the centroidal axis. Okay, so it is going to give us moment of inertia about any axis which is lying apart from the lamina, so that axis is AB here. So this theorem of parallel axis completes. So I think you have understood exactly what does it try to say us regarding the moment of inertia about any axis, if you want to take the moment of inertia of any lamina about any axis. Okay, so this is the standard formula developed. So moment of inertia about AB is equal to Ig plus AH square is the formula taken. So theorem of parallel axis is going to help us in solving moment of inertia problems. So now we will discuss theorem of mutually perpendicular axis. So here, say uh, consider a small lamina with area A, okay, having coordinates x y, okay, x y along OX and OY, okay, OX and OY. These two are mutually perpendicular axes on a plane section as shown in the figure there. Say consider a plane OZ perpendicular to OX and OY. Okay, so you are identifying it. So OZ is perpendicular to OX and OY. So now the theorem of perpendicular axis statement, what does it states is, if moment of inertia about x-axis, okay, that is ixx, and iyy, that is moment of inertia about y-axis, okay, ox and oy, be the moment of inertia if ixx and iyy be the moment of inertia of a plane section. Plane section is that lamina, right, in the figure. So moment of inertia of a plane section about two perpendicular axes meeting at O. Okay, the moment of inertia izz means moment of inertia of that OZ axis. Inertia, moment of inertia of izz about z axis, okay, perpendicular to the plane and passing through the intersection of xx and yy axis is given by, okay, is given by, you can see the formula, izz is equal to ixx plus iyy. What does it say? It is the summation of moment of inertia of xx axis and yy axis, okay, will give you moment of inertia of perpendicular axis, that is about zz axis. Okay, so this is how the theorem of mutually perpendicular axis is understood. So moment of inertia of a plane lamina about an axis perpendicular to the lamina and passing through its centroid is equal to the sum of its moment of inertia about two mutually perpendicular centroidal axes lying in the plane of lamina. Okay, so now we will try to understand polar moment of inertia. So what does it say? So polar moment of inertia of a plane area, okay, just imagine a plane area with respect to the axis perpendicular to the plane, okay, is called polar moment of inertia. So polar moment of inertia, first we know moment of inertia, right? Now what is polar moment of inertia? Now addition of polar there, right? Polar word is added to the moment of inertia. So polar moment of inertia of a body is moment of inertia of the body about its centroid axis, which is perpendicular to the plane of the body. Very easy, right? So normally it is given by capital letter J. Okay, it is indicated by capital letter J. Now what is radius of gyration? Radius of gyration, you can see the formula there, k is equal to under root moment of inertia divided by area, right? So a is nothing but a area and I is nothing but moment of inertia. So how it is defined there? A radius of gyration of the body is the distance from the axis of the reference where the whole mass is assumed to be concentrated. Okay, it means that it is nothing but the centroidal point, so as not to change the moment of inertia about the given axis. And this radius of gyration is represented by capital letter K. Okay, so this radius of gyration also can be defined in other terms, that is the distance from the axis at which all the elemental components of the lamina require to be placed so as not to change the value of moment of inertia about the axis. Okay, so the formula given here is under root moment of inertia ratio of moment of inertia to the area under root. Okay, so thank you students for patient listening. For further notifications and upcoming videos, subscribe the channel, like, share. Thank you.